Good afternoon, everyone. Welcome to the last session of the conference. In this session, we are going to present 5 wonderful papers on multimodal and cross-technology communications. Because one of our speakers has a flight to catch, so we change a little bit the presentation order. Let me introduce our first speaker, Mr. Chris Xiaonan Lu. Mr. Lu is currently a 4th-year PhD candidate at Oxford University, founded by Google DeepMind. His research aims to enable ambient intelligence for future IoT systems. Mr. Lu, you are welcome to start.
Okay, thanks for the introduction. Hello, everyone. I'm Chris. Today, I'm going to introduce how to use power line radiations to do indoor localization. This is a joint work with my colleagues from Oxford University, Shenzhen University, University of Warwick, and the Nanyang Technological University. Understanding users' location is a key enabler for smart spaces. By accurate localization, many context-aware applications can be realized to improve our life. Examples are navigation in hospitals, location-based advertising in shopping malls, and worker tracking in factories. Over the last decade, indoor localization technologies have reached a significant level of maturity. Not only we found many different modalities for localization, but proposed many advanced algorithms to improve the accuracy. However, achieving sub-meter accuracy is still very challenging, especially in large-scale sites. And if we have a look of the past Microsoft indoor localization competition, which is the most influential event in this domain, the winning team performance doesn't improve much with the increasing area of the test site by every year. In fact, despite of the algorithm advancement, the limitation of these modalities are still there and restrict the further performance gain. Examples are environment dynamics for RF signals, drifting issues for gyroscope, occlusion curses for optical sensors. As such, many localization systems adopt a multi-modal fusion to holistically resist the limitation of each one. And because of this, we never stop looking for new localization possibility to serve as another brick. Generally, we hope such localization modality bears 3 basic properties. First, this new modality has to be spatially distinct to provide enough location-specific information. Second, this modality needs to be temporal stable, otherwise no meaningful features can be extracted. Last but not least, we hope this is a cohesive channel that can be used for many scenarios and different environments. And in this work, we explore an overlooked possibility of using the built-in power line radiations for indoor localization. Power networks are very pervasive in modern buildings. To provide enough electricity, they are all over the building and densely distributed on every floor. These power networks supply AC voltages with an effective value of 220 at the nominal frequency of 50 Hz. Because of the alternating currents, the radiations from the power lines in a building will form an EMF, which is a superposition of different power line sources. As the radiation intensity decays with physical distance from the emitting power lines, EMF could have different lookings in different places. This motivates us to use EMF to do localization. For simplicity, in the rest of my slide, I'll use EMF to represent the power line EMF unless there is ambiguity. Let's have a close look on these EMF signals. We put our customized sensor in different locations, as shown in the left figure. And the right side shows the EMF 10 series. As we can see, EM signals in different positions have various shapes and different amplitudes. Considering the short distance between these test points, such observations is very encouraging for localization purpose. By using Fourier analysis, we found that the main components of EMF signal lies in the 50 Hz and its harmonics. This is reasonable because our measurement study is conducted in UK, while the local operating AC frequency is 50 Hz. This property of power line EMF is very important for us to filter out those noisy ambient EMF. After understanding the basic features, we look into how suitable EMF can be used for localization. As we focus on indoor scenarios, the impact of electric devices should be considered. By surveying 8 common devices in commercial buildings, we conducted a set of controlled experiments to investigate the impact of their operating status on the EMF signal changes. As we can see, EMF is not sensitive to most devices. Although we see fridge and microwave are strong disruptors in short range, their impact gets negligible when the distance are over 80 centimeters away. Such distance is safe, as in most of the time, the indoor occupants won't be that close to them. We further leverage the impact, investigate the impact of human bodies. We ask a researcher to handheld the sensor, and we record the EMF readings for 30 seconds. Then more persons join the experiment by standing half a meter away from the user, and we log the EMF readings for the same amount of time. The right side figure indicates that the nearby human bodies has little impact on EMF. This is as expected, as the wavelength of the 50 Hz EMF is very long, that can easily bypass small obstacles like human bodies. Besides the short-term tester, we also did some long-term tester. We walked around a test bed in 2 different seasons, and the result shows that the logged EMF traces after 6 months can be still similar. The above results imply the good stability of EMF, and now we turn our head to its location difference. We did the measurement by walking 3 loops in the previous test bed, and the left figure shows the EMF amplitude by every step, along with the drifted IMU odometry. The takeaway of this figure is that the location distinctness of EMF is sparse. Namely, at some points, they are quite different, but in many points, they are too smooth to be discriminative. So we devised a way to amplify the make them discriminative by utilizing the EMF sequence from 7 consecutive steps. The location difference can be amplified by this combination. This motivates us to use a chunk of EMF readings as features instead of a single-step snapshot. Another important observation is that we found such location difference of EMF can be somewhat picked up by the commercial microphones. We walked twice around the test bed and used the microphone to log the EMF readings around our walking. The figures show the extracted mains harm, namely EMFs, in the audios in different trials. As you may find here, although the audio EMF is not as informative as the case of a customized sensor, there are certain repeatability between these 2 readings. As we will discuss in the evaluation, such repeatability is able to help other localization modalities on smartphones. All right, now we are in a position to introduce how to develop the localization system based on our observations. Unlike traditional methods, which use a high-cost fingerprinting survey to build up the EMF feature map, we push ourselves to automatically develop the feature map with least human intervention. The rationale here is that given the co-recorded IMU odometry, even noisy, we could leverage some informative and similar EMF patterns to determine the same locations in different loops. And we call such location pairs as loop closures. With these loop closures, EMF fingerprints can be automatically developed. We propose a 2-step method to detect these 2 closures. In the first step, we profile the closest pair for every EMF sample. Each EMF sample here is a vector consists of the consecutive EMF readings in 7 steps. To address the issue of changing walking speed, we use a dynamic time warping for similarity comparison. Then, in the second step, we select out those most similar pairs and merge other closest samples that are associated with them. This 2-step method boils down the complex 10-series motif mining problem to closest pair searching, which can scale very well to large sites. Based on this detected loop closures and IMU odometry, we found we could formulate the automatic EMF fingerprinting as a SLAM problem. By doing SLAM, the underlying floor plane can be reconstructed, as well as a respective EMF feature in every position, namely the fingerprints. However, due to the smoothness of EMF, we found that some of the proposed loop closures are false positives. And if we directly feed these false positives to SLAM, the reconstructed feature map could be inaccurate. We therefore propose a method to validate the loop closing proposals before doing SLAM. The idea is that instead of completely trusting the EMF similarity, we could validate those loop closing proposals through their inherent spatial coherence. Specifically, given any pair of the loop closing proposals, we could have two subpaths defined by them. If both proposals are true, they should support each other and could form a clique after certain displacement. By contrast, if the proposals are false positives, their subpaths will not preserve the spatial property. For instance, here you can't make the two subpaths to form a clique, even after some certain displacement. We remove failed proposals, their associated points from our list. For validated loop closures, we do the following update. The update is based on the rationale that label points of the true loop closures are also very likely to be another loop closures. Therefore, we propagate the distance of validated loop closures to their neighbors. Each neighbor pair receives the propagated distance and updates their original distance at the rate of beta. The Gaussian mask here is to recede the far propagations. Given the new distances, we could update the closest point profile to detect new loop closing proposals. And then we iteratively repeat the loop closure detection, proposal validation, and the distance update until no new loop closing proposals are detected. Then we use these finalized loop closures to get an EMF feature map through SLAM. When we developed the feature map for online localization, we found that the computation latency is another challenge, especially in cloud-denied cases. This is because the EMF fingerprinting comparison is based on the dynamic time warping, which is inherently computational heavy. As a result, the online EMF localization can hardly be used for real-time applications, especially when you have a big fingerprint for large-scale spaces. But recall that the EMF feature consists of the signal chunk of several consecutive steps, and the signals within a few step distance are smooth, although such smoothness is charged for SLAM, but is trivial for latency reduction. Why is that? We leveraged this smoothness and designed a two-step specification pipeline. In the first step, we use the mean value and the standard deviation of EMF to prove in the searching region in the database. EMF fingerprints with quite different statistics won't be considered in the next step. Then in the second step, we zerify the elements in the EMF feature vector if they fall into a small region around the mean value. Because of the short distance smoothness, such specification can lead to consecutive zeros. And given the sparse feature vector, a modified DTW could adopt here to speed up the matching process. The trick here is like the modified or sparse DTW can skip consecutive zeros in the warping path to reduce the computation redundancy without precision loss. Please see our paper for more technical details here. Okay, let's get some actual results. We use two types of EMR receivers, including a customized sensor dedicated to sense the power line EMF, as well as a capsule microphone, which is a smartphone accessory. We conducted extensive experiments at 3 different sites in 2 countries, including a lab space, an office building, and a shopping mall with an area over 11,000 square meters. By comparing with other localization modalities, we found that EMF-based SLAM is better than other modalities. Particularly, we get the best performance when fusing the microphone with a geometric sensor, which implies the microphone EMF can be a complementary channel. We further examined the performance gain of loop closure curation. By comparing our method with 2 state-of-the-art baselines, we found that our proposed method is consistently better than them and is able to give 15 to 30% accuracy improvement. Given the EMF feature map provided by the SLAM, we evaluated the localization performance. In order to have a fair comparison, we didn't combine the IMU-based PDI here. We found that both customized sensor and the microphone plus geometric sensor can give us reasonable localization results, considering that the fingerprinting map is automatically developed and the experiment site is quite large. Above the results are promising. Lastly, we evaluated the efficiency. We compare our specification method with a baseline of constrained DTW, which is designed for faster DTW computation. We did experiments on 2 smartphones and Raspberry Pi 2 and 3. Overall, we found that our algorithm gives the most efficiency with a small accuracy drop. The speed up is as much as 20-fold when compared with a case of no specification. The localization time are around half second, which on all platforms, which can support many real-time applications. All right, let's summarize. In this work, we propose to use a ubiquitous powerline EMF as a new localization channel, a novel loop closure, and the iterative curation method is proposed to automatically develop the reliable EMF feature map. To enhance the localization efficiency in real-time applications, we proposed a feature specification pipeline to give a 20-fold speed up. If you are interested in my work, please visit my homepage.
Okay, let me introduce our second speaker, Mr. Kai Zhang. Mr. Zhang is a postgraduate student in the School of Software and Tianlist, Tsinghua University. He received his bachelor degree in School of Software, Tsinghua University. His research interests include visible light communication, blockchain, and so on. Okay, Mr. Zhang, you are welcome to start.
Okay, thanks to Professor Lu Su for the introduction. Hello, everyone. I'm Kai Zhang from Tsinghua University. I'm advised by Professor Zheng Yang. Today, I will present you our work, Quermo Code, a fully imperceptible screen camera communication system, with me and Chen Shu Wu as co-primary authors. This is joint work with Professor Chunyi Peng. Currently, it is reported that 65% of people skip online video advertising, mainly due to the intrusiveness. Delivering advertising content without tempering primary video itself will not only guarantee viewing experience, but also enhance user interaction. One common real-life example towards this paradigm is QR code. QR code especially occupies a small area on the corner of a screen and has extra information embedded inside. However, QR code is obtrusive to human eyes and affects viewing experience. QR code may overlay important video contents, especially in small monitors with limited screen spaces. QR code are mainly designed for device-to-device communication and is meaningless to human eyes. So what we hope is to make eyes and other information invisible to viewers to simultaneous viewing and communication. This necessitates hidden screen camera channel. What we hope is to embed data frame into primary videos unobtrusively, so that when the video is being played, human eyes cannot perceive the embedded data frame. Human eyes can only see the original video content, but we can still capture the embedded data frame with a high capturing rate camera, and then decode the encoded data scale. Related works have been done to enable hidden screen camera communication. For example, InFrame++ leverages low-pass fusion property of human eyes and embeds invisible data frame into videos by doing complementary lattice modification. Texture code only embeds in textured regions to improve the invisibility. There are mainly 3 key conflicting goals. They are invisibility, reliability, and throughput. However, these 3 key goals can be conflicting. For example, we can increase lattice modification amount to achieve more reliable data transmission, but more flickers may be perceived by human eyes. So these goals can be conflicting, and while previous works usually made a trade-off among them, our work, Chroma Code, aims to achieve all the three key goals while maintaining watching experience to users. So this slide shows the overall architecture of our work, Chroma Code. The original video is firstly encoded with concatenated encoding and then modulated to generate a data frame. The data frame is then embedded into primary video with adaptive embedding so that when the video is being played, human eyes cannot perceive the embedded data frame. But we can still get the embedded data frame with the camera and then do demodulation and decoding to retrieve the embedded data. Firstly, let's review how hidden screen camera channel is achieved. This is achieved by doing complementary lightning modification. More specifically, we leverage the low-pass flicker fusion property of human eyes. Human eyes cannot perceive flickers with frequency higher than 100 Hz, but instead can only observe the average lightness. So we can generate high frame rate complementary frames with complementary lightness modification to embed invisible data frame into videos. But we can still use a high capture rate camera to capture the embedded data frame and then decode it. However, the hiding quality is not good enough in related works. We firstly achieve fully imperceptible with some color space studies. Colors are not objective existences, but are perception in the visual center of human brains. To show colors in electronic devices, color spaces were developed to model human vision system. There are exactly 3 kinds of cone cells in human eyes, shaping the trichromatic human vision system. And the first color space, CIE-RGB, was built from human vision experiments. However, CIE-RGB has chromaticity distributions in negative axis, which may lead to inconvenience for calculation. So to solve this, CIE-XYZ color space was built by doing a linear transformation to CIE-RGB color space. McAdam ellipses are obtained from CIE-XYZ color spaces with human eyes experiments. Each ellipse is a region that contains all colors which are indistinguishable to human eyes. However, colors outside of the ellipse are distinguishable from the center, the color at the center of the ellipse. However, as the obtained curves are ellipses instead of circles, they prove that color differences are not in proportion to Euclidean distances of color vectors in CIE-XYZ color space. So CIE-RGB, CIE-XYZ, and all their linear transformations, for example, YUV, are non-uniform. To deal with this, efforts have been made for decades to obtain uniform color spaces. We compare non-uniform and uniform color spaces with their hue and lightness palettes. There are 3 annuluses in each palette. The middle annulus has lightness L. The outer and inner annuluses have lightness L plus delta L and L minus delta L. We can observe that in non-uniform color spaces, the color differences are not uniform. For example, color differences are more obvious here, while color differences are less obvious here. For color palettes in uniform color spaces, the color differences are more perceptibly uniform. Uniform color spaces suit human vision system better. Therefore, we choose uniform color spaces for lightness modification. More specifically, we choose CIE-LAB uniform color space along with CIE-DE 2000, the most latest and most accurate color difference formula currently available. The CIE-DE 2000 color difference formula inspires us that instead of choosing a fixed amount of lattice changing amount, we should firstly choose a fixed desired color difference amount, and then calculate the desired lattice changing amount. So this shapes our outcome-based lattice change derivation based on lattice of single pixel. And what's more, as previous studies show that lattice changes are more noticeable in smooth regions, while less noticeable in texture regions. So we further calculate the texture complexity and decrease lattice changing amount in smooth regions based on their texture complexity to get our final lattice changing amount. To achieve reliable high-throughput transmission, we need to deal with challenges including projection distortion, Moore pattern, and rolling shutter effect. Projection distortion makes the shape of our data frame into an irregular quadrilateral. Moore pattern leads to random noises, and the rolling shutter effect leads to burst errors near the rolling shutter effect line. And also, rolling shutter effect makes the captured frame by camera in fact may contain two neighboring frames of original videos. So to deal with these challenges, we elaborately designed our data frame. We use 4 frame embedding and 1 cell encoding 1 bit to achieve high throughput. And we use concatenated encoding that takes the advantages of both read-Solomon code and convolutional code. We also use interleaving techniques to deal with burst errors to transform burst errors into random errors. We also eliminate various channel distortion, for example, with projection transformation and with Moore pattern removal. Our evaluation of QAM code mainly contains 2 parts. One part is a user study part that measures the user perceived invisibility. The other part is a data transmission benchmark that measures the throughput and BER. We select a group of videos as primary videos for our evaluation. One key consideration during video selection is to find a set of videos that a set of representative videos with various characteristics. For example, incorporating both plain and textured frames, involving both sharply and gradually changing scenes, and containing both dark or bright scenarios, and also covering both high and or standard video qualities. We firstly measure the results on different video sources. The experiment's results show that videos with higher texture complexity usually achieve better usability, but also lower raw throughput and higher BER. We compare CIE-LAB uniform color space with 3 other non-uniform color spaces. We can observe that CIE-LAB uniform color space indeed yields significantly better invisibility than the other color spaces without downgrading the data transmission performances. We measure how distance and angle affects the invisibility and data transmission. We can see that invisibility is better at larger distance, but throughput and BER get worse at larger distances or angle. However, larger data cell sizes or screen sizes will improve data transmission performance over long distances. We compare QAM code with 2 state-of-the-art approaches, in-frame plus and texture code. As shown by the plus markers, although texture code achieves graceful invisibility consistently, its throughput is rather low because it does not embed in plain regions. And as shown by the circle markers, Iframe++ has rather high throughput, but its invisibility is still not good enough. And as shown as the square markers show that our work, Chroma code, achieves superior performance over previous schemes in terms of invisibility, throughput, and BER. So to conclude, we present Chroma code, a system that achieves all three key goals on unobtrusive, high-rate, reliable screen camera communication. We prototype Chroma code and evaluate it by experiments. The results demonstrate its superior performance over previous schemes in terms of invisibility, throughput, and BER. That's all. Thank you.
Let me introduce our third speaker, Mr. Ke Sun. Mr. Sun is a third-year master student in Nanyang University. He will graduate from Nanyang University next summer. His recent research mainly includes ultrasound-based HCI systems, device-free tracking, and biometric-based applications. He's going to apply for a PhD program this year. And if you have any opening, please contact him. Okay, Mr. Sun, you're welcome to start.
Thank you for the introduction. And this is Ke Sun from Nanyang University. Today, I will present our recent work, V-Skin, sensing touch gestures on surface of mobile device using acoustic signals. The co-author of this work, Ting Zhao, Wei Wang, and Lei Xie, are all from Nanyang University. Nowadays, touch gestures has becoming a standard user interface for mobile device. We always use different kinds of touch gestures, such as swiping, scrolling, and tapping to control the mobile device. However, due to the high cost of touch screens, this touch gesture sensing is always limited on the front of the surface, which will lead to many bad experiences and problems. For example, when we are surfing on the social media, we always like to use the gestures to control the content. However, these gestures will also block the touch screen, which will lead to the occlusion problems. Also, the touch screens always confuse user intention. For example, when we use the touch gestures to control the touch screen, it is difficult for touch screens to distinguish whether we want to click the hyperlink or just want to scroll down the page. Furthermore, due to the small space of touch screens, when we play in the video game on the mobile device, there are always too many buttons on the screen, which will lead to bad experience. So, if we can enable the touch gestures on all surfaces of the device without any hardware modification, our work focuses on these problems, and we enable different kinds of touch gestures, such as scrolling, swiping, and tapping to control the mobile device. We think that this will enrich user experience in the future. Our basic idea is to utilize the built-in speakers to transmit the ultrasound signal and then use the microphone to receive these signals. When we performing the touch gestures on the back of the device, we will detect the touch and sense the touch gestures. Let's have a brief look on the propagation models of the acoustic signals. There are mainly three paths for the acoustic signals. The first path is called the struct-borne path, which means that the sound transmits through the struct-borne body and then directly arrive at the microphone. And the second path is called the line-of-sight air path, which means that the sound transmits into the air and then directly arrive into the microphone.
The third pass is called the reflected air pass, which means that the sound is reflected by the finger or other block and then received by the microphones. So when we perform touch gestures, there are many two paths will change. First, the struck bone path will change because our touch changed the vibration patterns. So we can use the struck bone sound patterns to detect the touch. Also, the reflected air paths will also change their distance because of our finger movement. So we can use the reflected air path distance change to measure our finger movement. However, the biggest challenge is that how to separate this struck bone sound, the air bone sound, and other different kinds of multipass. The basic idea is that this sound have different delay. For example, the first sound is the struck bone sound because the struck bone sound have higher speed than the air sound. And as a result, they have the lowest delay. And then the left-side air sound have the median delay because they transmit into the air and they directly arrive at the microphone. Finally, the reflected air pass sound have the longest delay because they have long distance to travel. However, this delay is too small for us to separate. The delay difference is only 1 millisecond, less than 1 millisecond. So we have to carefully choose the transmission signals to separate these different sounds. As a result, we choose explicit signals which have high resolutions, high SNR, narrow inaudible range with phase information. We choose the JC sequence as the base signals. This sequence is a chip-like polyphase sequence, so we can obtain the phase information during our sensing. One of the most important property of JC sequence is that they have near optimal audio correlation function. They have narrow main lobe width, high gain, and low side lobe. However, although we choose this JC sequence as the baseband signals, these sounds are still mixed together. So we use the cross correlation to estimate the impulse response. And we can see in this figure, the peaks of impulse response indicates one of the propagation paths. So let's have a brief look on the impulse response of both the microphones. First, there arrive a peak, which means the struck bone sound, because struck bone sound have the lowest delay. And then there is another peak for their left-side air sound. However, for the bottom microphone, the distance between the microphone and the speaker is too small, so they only have one peak. And then the reflected air sound arrive. They are a little blurred because there are many multi-paths for reflected air sound. So we separate this sound into two categories. The first category is the path with static delay, which means the struck bones path and the left-side air path. They merely change their delay during the touch gestures. So we calibrate this delay at the beginning of the system. And then we dynamically change the delay of reflected air path because this delay are always changed during our sensing by our finger movement. The second challenge is that how to measure the path coefficiency of single path, which means the single delay. The path coefficiency here means that the IQ trace for certain delay. When we obtain the IQ trace, we can obtain the phase and amplitude. We can use the phase change to determine the path distance, and we can also use the amplitude to determine the path strength. However, in traditional method, one flip can only obtain one result of single single pass. If we look at the black line in the figure, we can see that the phase change is not like a circle, but like a triangle. This is because that the path coefficient sampling rate is not high enough, and they can't capture the fast movement. And this is because they can only obtain one result for one frame. Just like this, they always perform impulse response estimation for one frame, so they can obtain one result for one frame, and they always get all the delay result, which will cause high computational cost. However, in our method, we found that the CC sequence have a constant amplitude, so we can perform the moving window on the basebank demodulation. And we can have high sampling rate. We can also choose the interesting delay that we are interested in, and which will save the computational cost. The second challenge is that how to measure the movement and detect the touch. The movement measurement is based on that the reflect path delay will change when we're moving. So when our finger approach the microphone and the speaker, the reflect path delay will change slowly. It's just like in this heat map, we can find that the finger move away and then move towards in this heat map. And however, this result is really too coarse-grained. So we have to use the fine-grained method to determine the movement distance. So we only select the delay of the reflect path based on the differential impulse response. And then we still use the phase change to measure the the finger movement. We use the EKF to mitigate addictive noise, and then use the curvature-based estimation to estimate the phase change. For the touch detection, we found that touching on different positions on the back of the mobile device have unique patterns for struck-bound sound pass. So we use the delay of the peak in the differential IR estimation to determine the touch position. Our implementation can work as an app on commercial mobile phones, and we use both speaker and microphone to enable touch gestures such as scrolling, swiping, and tapping. We also conduct different kinds of experiments on 4 different kinds of smartphones. Our finger movement accuracy can achieve less than 4 millimeters, and we can achieve, because of the high sampling rate, upsampling method, we can achieve movement distance with high accuracy for speed from 2 centimeters per second to 12 centimeters per second. Our finger movement is also robust to the other interfering movements. For example, when the hand is pushing and pull at 10 centimeters away from the microphone, we can still achieve 5 millimeter accuracy. So for touch detection, we can achieve 98% at the back of the phone, and we can also achieve 88% for classifying touch positions at the back of the phone. We also perform 2 case studies. The first study is for the scrolling gestures. Our work can achieve only 2 milliseconds slower than the touch screen. And for the swiping gestures, our work can achieve only 100 milliseconds slower than touch screens, which means that this skin can have comparable ability to the touch screen, and the users can merely perceive the latency. In conclusion, we build a system that uses acoustic signals to sensing the touch gestures on all surfaces of a mobile device by separating the struck-bound and airborne sounds. We enable different kinds of touch gestures, such as swiping, tapping, and scrolling. We measure the fine-grained gesture measurement, and we can work as an app on a mobile device. Thank you. That's all. Thank you.
Let me introduce our fourth speaker, Mr. Lei Yang. Mr. Yang is currently a research assistant professor from Hong Kong Polytech University. His research interests include RFID, Internet of Things, wireless sensing, and mobile computing. Okay, Mr. Yang, you are welcome to start.
Thank you. Thanks for the introduction. It's our great honor and pleasure to introduce our recent work. Okay, my name is Lei Yang, and I co-authored with my student. Yin Zheng is a second-year PhD student. Chung Zhenglin is a postdoc fellow. We are from the Hong Kong PolyU. Okay, the title is Cross-Frequency Communication, Near-Field Identification of UHF RFID with Wi-Fi. Okay, first of all, please allow me to briefly introduce the background of the RFID system. The typical RFID system composed of three parts. The first part is RFID reader, right? It supplies energy to RFID tags. The second component is RFID tag. We can attach RFID tag to any object and to identify those objects. And the third part is the communication protocol, right? It's called as the AL interface protocol. Okay, this is a member from the report. From the ID tag report, we can see that there's almost 10 billion tags has been sold in the last year. So this number is so huge. We can see that the RFID has become one of the most important roles in the Internet of Things. Okay, actually, on the market, there are two leading auto ID techniques. One is the barcode, and another is RFID. Okay, this picture shows that the RFID is much more efficient than the barcode, right? Because barcode uses the light. At each time, the RFID reader can identify a single barcode tag at each time. But RFID uses the wireless signal, so it can identify the RFID tags, multiple RFID tags at each time. So RFID is expected as a perfect replacement of the barcode. But the reality is that to date, the RFID system are still limited to a very small number of industrial areas. For example, the warehouse, the hospitals, and the logistics, right? We seldom see the RFID tags in our supermarket, right? So we can see that RFIDs are not so popular in the customer-oriented market. So why? We know that today's smart devices are so powerful and contain so many different sensors, but unfortunately, none of these sensors can be used, all the wireless transceivers can be used to identify RFID tags. So we believe that one of the most important reasons that RFID are not popular in the customer-oriented market is because RFIDs are not supported by the current smart devices, right? Okay, that is because the RFID operated at the spectrum of the 800 and 900 megahertz. And none of the wireless signals at the smartphone can work at this spectrum. So to resolve this problem, industry had made some efforts. For example, they proposed some trade-off solutions. Here, for example, the first product is from the Impinj company. This is a holder. Well, the user can insert his smartphone into this holder and then use the holder to scan the RFID tags. The second product is from the Alien company. It functions similar to the first one. And the third one is from the Carrier company. It is a very small mobile reader module. The user can insert this module to the smartphone through the headphone jack and manipulate this model reader through the acoustic signals. Okay, however, after years, this trade-off solutions has achieved minimal progress. Why? Because they either actual the hardware or increase the deployment complexity. So today, I'm going to introduce our solution. Our goal is that we allow the commercial smart devices to identify the commercial RFID tags without adding any extra accessories or changing existing hardware. we named our system Wi-Fi, okay, tag emulated Wi-Fi. Okay, so from a high level, our Wi-Fi contains 3 actors. The first actor is the reader, second is the RFID tag, the third one is our smartphone. So from a high level, the Wi-Fi converts all these tags into the Wi-Fi APs. These APs broadcast the Wi-Fi beacons. So this beacon, oh, by the way, the beacons contains the SSID. This SSID is exactly the same as the corresponding text, the EPC. EPC is the electronic product code. So the users or customers can identify these tags in the way of discovering the new APs. For example, in the right figure, we just use a built-in iPhone AP scanner to identify the tags. Okay. So, unfortunately, we cannot play the video. Actually, we have demonstrated our solutions last night. Many visitors has observed our system, but it's okay. And so to achieve this goal, we have encountered so many challenges. One here, I just introduced two main challenges. The first challenge is apparently, right? How can the UHF tags be audible to the Wi-Fi receivers? As I have mentioned, right, the RFID system operates at the spectrum of the 800 megahertz and the 900 megahertz. But the Wi-Fi chipset operates at the 2.40 ISM band, right? So there is almost a 2G frequency gap. So our first task is to achieve the cross-frequency communication. This picture shows the internal structure of the RFID tags. It contains so many rectifiers. Rectifiers has a non-linear effect. Okay, because of the absence of the non-linear treatment in RFID tags results in the harmonic backscattering. What is harmonic backscattering? Okay, this picture shows our result of our experiment. In this experiment, we query a tag, not a commercial, of course, the commercial RFID tag, with at the 920 megahertz. And this figure shows the spectrum of the backscatter signals reflected from tags. We can see that the signals not only specs at the fundamental frequency, of course, the fundamental frequency is 920 megahertz. It also backscatters at harmonics. For example, the third order harmonics is at the 2.70 hertz in this experiment. So imagine that if we query the tag at 800 megahertz, and we should observe the third order harmonic at the 2.4G, right? So this harmonic backscattering inspires us to achieve the cross the frequency communication. This is our solution. We use two frequencies. The first frequency is the primary frequency. It used to power up the tags and drive the inventory procedure. Okay, and at the same time, we also use the secondary frequency to stimulate tags to reflect Wi-Fi beacons. Okay, this works at the 800 megahertz. As a result, we can observe the signals at the, for example, the 920 megahertz, 800 megahertz. Also, of course, important that it will backscattered at the 2.40 hertz. Okay, that is our solution. So this we have bridged the frequency gap. The next question is that the Wi-Fi chipset cannot recognize the packages from the RFID systems because of the incompatible protocol, air protocol, right? The Wi-Fi chipset cannot recognize the RFID package. So the next task is to achieve the cross-protocol communication. So this is we designed the system in terms of two layers, the physics layers and also the MAC layers. Firstly, I introduced the physics layer. Okay, this is the background of the RFID backscattering, right? The reader transmit a singleton CW. CW is a continuous wave to the tag, and the tag modulates its EPC by changing the amplitude of the CW. Right, so the backscattering is based on the ASK, right, amplitude shifted keying. Now this is our solution because we want the tag to reflect the Wi-Fi beacon. So we modulate. We don't send the singleton CW. Instead, we modulate the Wi-Fi beacon on this CW at the 800 MHz. As a result, this beacon will be reflected at two frequencies. The first frequency is a fundamental frequency, 800 MHz. It doesn't matter because we don't care it. The next is the frequency is 2.4G because of the harmonic backscattering. So we can see that the way from the high level, we can see that the tag can backscatter the Wi-Fi beacons. So okay. I will accelerate, speed up my talk. I thought I have 50 minutes. Okay. So that's the next question is the MAC layer design, right? We must seamlessly integrate our solutions with the Gen 2 protocol, right? There are three timing requirements. The first requirement is that the reader should acquire the EPC already because we real-time assembling the beacon, the Wi-Fi beacon with the EPC, right? We use the EPC as the SSID. The second constraint is that we must broadcast the Wi-Fi beacon exactly during the window. What's the window? The tag backscattered is the EPC because most of the time the tag keeps silent. We must broadcast the beacon when the tag reflect is the EPC, right? So that we can get the harmonic backscattering. Okay, of course, the third one is that we must guarantee that only one Wi-Fi beacon is reflected at any given moment in order to avoid the collisions. Okay, this picture shows the whole procedures. We just add a new step that is retransmission. We just transmit our Wi-Fi beacons during this phase. Okay, the second picture shows the baseband signals that acquired by our Wi-Fi Type-5 reader. Okay, next I briefly introduce some implementations, details, and evaluations. Right, we use USRP to implement our Type-5 reader, and also we test our system across 6 types of the commercial readers and also 7 types of Wi-Fi chipset. Okay, this picture summarizes the comparisons to the related work. For example, this is 3 items from the industry that I have mentioned in the previous slide. We can see that the industry solution can achieve the maximum range of the 1.5 meters if you use a mobile reader. Okay, another solution is we can use the HF NFC, right? NFC is used for the access control or payment, right? And the NFC can achieve the maximum range is less than 1 meters, and this is our solution. The maximum range is about the 2 meter. So we can see that the Type-5 operates at both RFID and Wi-Fi spectrum, but performs comparably to the commercial mobile readers. The most important, it can support the rating of those smartphones. And this picture shows the beacon strength as a function of the distance. We can see that it demonstrates a very good linearity. Why we use this? Why emphasize this? Because so that we can use a proximate-based localization. Imagine that if we want to identify a tag in the supermarket, there are so many goods, products are so many tags. We just put our smartphone close to the product, and you can get the EPC, right? And then you can get the more information from the internet with the EPC. And this also shows the good put, right? Our Type-5 can achieve the very good median. The good put is up to the 90%, 3%. Of course, we also test our test over the diverse Wi-Fi receivers. Okay, this is the application studies where, for example, we can allow the readers or users to get the more information just by putting his smartphone to the book right in the library. Or most important, because beacon is modulating the wireless signals, so it can pass through some obstacles. Okay, in conclusion, in this work, we introduced the Type-5 system. The Type-5 leveraged the RFID tags harmonic backscattering as a second channel to achieve the coarse frequency communication. And secondly, we proposed a new type of CTC, coarse technology, the technical, that allows the tags to communicate with Wi-Fi, right? And third, that we implemented the protocol and with also present demo. Luckily, we are giving the best demo award runner-up last night. Okay, thanks very much. That's all.
Let me introduce our last speaker, Mr. Wenchao Jiang. Mr. Jiang is a fifth-year PhD candidate in the Department of Computer Science and Engineering at the University of Minnesota under the supervision of Professor Tian He. His research interests are broadly in IoT with focus on harmonizing heterogeneous wireless networks and embedded systems. He's interested in making practical systems on commodity devices. Mr. Jiang is currently on job market, so if there are any faculty or researcher position in your institute, please contact him. Okay, Mr. Jiang, you are welcome to start.
Okay, thank you for the introduction. Today I'm glad to be here to present my work, Achieving Receiver-Side Cross-Technology Communication with Cross-Decoding. I'm from University of Minnesota. This is a joint work with my collaborators, So Ming, Zhi Jun, and Professor Tian He. We have witnessed the growing of IoT. The IoT market is expected to be 4 times huger to the year 2020 than the year 2015. And also in North America, the IoT market is expected to reach 550 billion till the year 2022. A fundamental technology of IoT is the wireless technology. The wireless technology keeps evolving with the coming of 5G. And the evolution of wireless technologies brings the diversity of wireless technologies. We can see there are diversified wireless technologies in all the ISM bands. For example, in the sub 1 GHz, there are Sigfox, LoRa, and NB-IoT. And in the 2.4 GHz, we have the popular Wi-Fi, Zigbee, and Bluetooth. And in the 5 GHz, we have LTE and Wi-Fi. The diversified wireless network is good for satisfying different needs, but it hinders the collaboration of wireless technologies. But in some scenarios, we do need the cooperation of wireless technologies to fill complex tasks. For example, the Zigbee network is good for building the sensor network to connect devices like a thermostat and the smoke detector. However, a user may want to use their smartwatch, which only has Bluetooth radio, to have access to the sensing data. And the sensing data may be uploaded to the cloud with the Wi-Fi or LTE network. We can see in such scenarios, we need the cooperation and the communication between heterogeneous wireless technologies. Then how can we do that? Previously, we can only based on the multi-radio gateways. However, the gateways has a limitation in the facility cost and not very support the mobile scenario. The recent advances propose the cross-technology communication, or CTC for short. It do not have additional facility costs and well suitable for the mobile scenario. Let me have a review of the state-of-the-art CTC technology. Early studies of CTC technology are based on the coarse packet-level information. They use information like the packet length and the beacon intervals to build a connection. Recent advances make use of the physical layer information, such as the modulation and the demodulation of wireless technologies. The state-of-the-art physical layer CTCs are commonly based on signal emulation at the transmitter side. For example, if we want to send a target packet, we first look at its signal in the air. Then we modify the input bits to make the output signal mimic the target signal. By doing that, we successfully construct a target packet to the receiver. However, one limitation of signal emulation is that the transmitter must be a high-end device. because high-end device has a high degree of freedom for signal emulation. Then it raises the natural question, what can we do when the transmitter is the low-end device? Here we propose XB to solve this question. We propose to move the complexity to the receiver side. We do cross-decoding at the receiver side. Let's give you an example. The transmitter is the low-end device, so it just sends signal in its own modulation. That means it don't need to, there's no changes at the transmitter. But at the receiver, we can do cross-decoding based on the data bits yield from the native demodulator. And from the data bits, we want to derive the target packet. Okay, let's see what's the feature of the design. And first, we enable physical layer CTC from a low-end device. It actually fills the gap in current studies. And it also requires no changes at either the ZigBee transmitter or the Bluetooth receiver. That means it's compatible to the current standards and can be deployed to billions of devices. And also, by using cross-decoding together with signal emulation, we form closed-loop physical layer CTC. That is essential for building reliable CTC network, because by having the feedback, we can send the acknowledgement of the packets. Let's take a look at the designs. First, I want to introduce the technical challenges. The technical challenges comes from the heterogeneous physical layers. The ZigBee device is based on the OQPSK modulation, while the Bluetooth low energy or BLE device based on the Gaussian frequency shift keying. And the other challenge is that we are supposed to use only the data bits from the demodulator. We cannot have direct access to the raw sampling. Then how can we do that? The opportunities for the solution is that there's the relationship between ZigBee's OQPSK modulation and Bluetooth and GFSK modulation. And the BLE device uses frequency deviation to indicate bits 0 and 1. The frequency deviation can be also transferred to the rate of phase shifts. Then we can, based on the phase shift, to build a communication between these two devices. Let's have a brief review of ZigBee's OQPSK modulation. A ZigBee symbol is the minimum unit of ZigBee packets. It consists of 32 chips. The odd chips, which is the white bits, it forms the in-phase signal. And the even chips, which is the black bits, forms the quadrature signal. And they add up to form the ZigBee physical layer signal. Then let's see how the BLE receiver decodes such signal. The BLE device will cut every 1 microsecond signal. Then it calculates the phase shift of the 1 microsecond signal. For example, here we have 3 time stamps, like T1, T2, and T3. We calculate the phase shift from T1 to T2, which is positive, from T2 to T3, which is also positive, and finally we have a positive phase shift, which indicates the BLE bit 1. However, in another case, such as that in this case we observe inconsistent phase shifts. From T1 to T2 it's positive, while from T2 to T3 it's negative. And finally, the overall phase shift is 0. But we notice that this is only in the ideal case. In practical system, it seldom happens. Let me tell you why it is the case. That's because the Zigbee packets cannot be well synchronized to the BLE sampling. There are always some sample offsets there. And because of the existence of sample offsets, we can see the positive phase shifts will be larger than the negative phase shifts. And finally, we can derive the result as the BLE bit 1. We also have other designs, such as how to penetrating the access address and how to do data whitening, how to do protect the receiver ID, and how to do the association between these two devices. You can refer to the papers for details. Let's take a look at our evaluation. We have implementation on both USRP and commodity BLE devices. And we did extensive experiments with various settings. First, we compare the data rate. The XB can achieve a data rate 1.7 times larger than VB. And also, it's achieved, and the data rate is also about 85% of the standard Zigbee data rate, which is the highest data rate we can expect. I have to emphasize that we compare with VB not because we want to show we are high in data rate, because VB is based on Wi-Fi to Zigbee. It's different technology. We make the comparison here just want to show that our cross-decoding can achieve comparable data rate with signal emulation, so that we together can form closed-loop communication. We also implemented the closed-loop communication between Zigbee and Bluetooth. And the Zigbee device will sending sensor data, while the Bluetooth will reply acknowledgement if it successfully receives it. Our experiment showed that the BLE device will successfully acknowledgement 95% of the packets. And let's see a demo. In the demo, the Zigbee device is broadcasting sensing data, while the Bluetooth device will collect data and show it on screen. Oh, sorry. Can I play it? Yes. In the demo, we try to change the sensing data by covering up the Zigbee device, or by using a flashlight to flash on it, and then we can see the change of light in real time. To summary, XB is the first to solve the CTC from a low-end device to a high-end device, and it can help to form a closed-loop communication with the signal emulation technique. And we implement the system on commodity device and show as the work demo. Also, our ongoing work is how to improve the data rate to reach the standard Zigbee data rate, and also how to generate the idea to other standards such as Wi-Fi and LTE. Thank you.